Yeah.
What should I do? Share the slide?
Yeah, can you share your slides, please?
Can you see?
Yes, great.
And may I start?
Yeah, could you just make it full screen, please?
Okay, I'm going to start. First of all, Martin, welcome to the 60s. And I'm going to talk on constructive theory of uniformity and its application to integration theory, which I promised Martin, I think at Dagestoo, January last year, almost 2 years ago. Okay, so it is a little bit tight. So I'm going to start with motivations. Bishop wrote in his book as follows. So something that to illustrate this point, consider the concept of a uniform space as developed in and he introduced uniform spaces using a family of pseudometrics. But he said a uniform space at first sight appears to be a natural and fruitful concept for constructive mathematics, promising substitute for the concept of a topological space. But he is very negative. In fact, this is not the case. Okay. So, but topology on the space L infinity and a strong topology on the dual space of a norm space are given by norms, that is metrics. Constructively, they are uniform topologies, but are not given by any family of pseudometrics. Therefore, we need a more natural framework for defining the notion of uniform space. And as an application of the framework for uniform space, we consider integration theory. And one of motivations, Lebesgue developed his integration theory was to make integration the limit commute, which does not hold for Riemann integral. And the integral is based on so-called Lebesgue measure. And measure is defined on sigma algebra, which is closed under the complementation. The lack of law of exclusive measure brings us a difficulty. Bishop overcame the difficulty by introducing the notion of complemented set and developed measure and integration theory. But the original motivation is concerned with the topological notion of a limit. So as far as we are concerned with convergence theorem, such as monotone and dominated convergence theorem, we may be able to constructively deal with them topologically without invoking the notion of measure and notion of complemented set. Bas-Peters took an approach using Bishop's notion of a uniform space. That is the family of pseudometrics. And preliminarily, so we are going to work within constructive set theory, ECST. ECST are based on intrinsic predicate logic with equality and has the set theoretic actions, extensionality, pairing, empty set, union, replacement, and bounded separation, that is separation for bounded formula, and strong infinity. So in ECST, we can define the ordered pair using pairing and Cartesian product using replacement and union. And in addition to these actions, we assume exponentiation action, saying that the class of function from a set A into set B is a set. And this is the notation. We write home I prime, where I prime are preordered set. Home I prime for the set of monotone functions between I and I prime. And preordered set is directed if underlying set is inhabited, and there is the monotone function which gives upper bound of 2 elements. And setoid or bishop set is a pair of set and equivalence relation on the set. And for two setoids, function is a setoid mapping if it satisfies extensionality for the equivalence relations. And the two setoid mappings are identical, is given in this way. And also we can define an injection just by replacing equality by corresponding equivalence relation. And also we can define product of setoid in this way. And we are going to introduce uniform spaces. First, we are going to introduce a uniform structure on a setoid, which is a triple consisting of a directed preordered set Ix, which corresponding to ontologies, and the function, monotone function rho x, and the relation, forcing relation between square of x and Ix. And the first condition corresponding to the uniform space is T1, a kind of separation action. And the second says that the forcing relation preserves the equivalence relation. And the third is forcing is symmetric. And fourth condition says that correspond to the this is the, so for example, entourage A is a subset of entourage B, other direction. Entourage A is a superset of entourage B, then XY is in entourage B, then XY is in entourage A. And the fifth condition correspond to, in a metric case, triangle inequality. And a uniform space is a setoid equipped with a uniform structure. This is an example for a pseudometric on a set. We can define equivalence relation in this way, and then we can form a setoid. And also, for this setoid, natural number and rho x and force x defined in this way is a uniform structure, okay, on a setoid. And also we are going to introduce so-called net or Moore-Smith sequence, which is a function from a directed preordered set into a setoid. And if J is the set of natural number, linearly ordered set, is called a sequence. And if the setoid has a uniform structure, then a net converges to an element X if there is a modulus such that as usual condition hold. Okay. And the cosinet is also defined usually, but with modulus. And the constant function j to x, x is an element of x, is a cosinet with any modulus. And we can show that every convergent net in a uniform space is a cosinet. And next we introduce uniform continuity. A function f is uniformly continuous if there is a modulus such that usual condition hold. And uniform isomorphism is a uniformly continuous mapping which has an uniformly continuous inverse. Okay, and we write in this way, and we can show that every uniformly continuous function is a setoid mapping, and uniformly continuous function maps convergent net into convergent net, and cosinet to cosinet. And also we can define product uniform space in this way. Product of two uniform structures. And for the space of net, we can introduce an equivalence relation in this way. X and Y, bold X and bold Y are net. Then this relation is an equivalence relation. And we can have a setoid. And also, we can define uniform structure on the space of nets in this way. Uniform structure consists of IX. IX is in an original uniform structure. Rho X to the 2 and forcing relation defined as above. Then we can make the space of net a uniform space. And we can define a function from the original space X into the net space, which maps X to the constant net X, which is uniformly continuous setoid injection, and also eta X to the J composed of X converging to X, bold X, in the net space for all cosinet. And regular net is a cosinet on a directed preordered set IX with modulus identity. X tilde be a setoid consisting of all regular net inherited equivalence relation from the net space. And also, we can make X tilde a uniform space by defining forcing relation induced by the net space as follows. And we write just eta X for eta X IX. And then uniform space is complete if eta X is a uniform isomorphism. And then we can show that every cosinet in a complete uniform space converges. And the completion of a uniform space is complete. And for two uniform space X and Y, x tilde times y tilde is uniformly equivalent to x times y tilde. And x times y is complete whenever so x and y. And also, I'm going to extend the notion of uniform continuity to local version. Function is locally uniformly continuous if there is a function called the family of local moduli such that the following condition hold. Okay? And then every locally uniformly continuous function is a setoid mapping, and locally uniformly continuous function maps convergent sequence to convergent sequence and coordinate to coordinate. And also we can show the following. If there is a uniformly continuous function from x to y into y, then we can lift up that function to f tilde, which is from x tilde to y tilde, such that this diagram commute. And also we can show that f tilde is unique in this sense. Okay? And then we are going to introduce topological vector spaces and lattices. Vector space is defined usually, but for the condition or actions, we use equivalence relation instead of equality. For example, function space on the unit interval is a vector space. And also, linear functional is a linear mapping from x to the reals. Okay. Topological vector space is a vector space equipped with a uniform structure such that first, the addition is uniformly continuous. And second condition corresponds to neighborhood of zero is radical or observing. And third condition corresponding to neighborhood of zero is circled. Okay? As usual, classical definition, this is the same as usual definition. And let X be a topological space, then the inverse is uniformly continuous, and the scalar multiplication is locally uniformly continuous. And also, if X is a topological vector space, that so is its completion. And we are going to introduce topological vector lattice. Semi-lattice is defined as usual, but replacing equality by the equivalence relation. And then we can introduce the canonical partial order as usual. And vector lattice is a vector space such that which is a semi-lattice, and the join operation satisfy the two conditions. Okay, and a vector lattice is ordered vector space, which lemma 18 said the vector lattice is ordered vector space. And as an example, first note that function space is a vector lattice with a join defined as follows. And let C01 is a set given by consists of pairs of uniformly continuous function and its modulus. And then we can introduce equality, just use the equivalence relation on function space. Then the setoid is a vector lattice. And also, in vector lattice, we can define a meet in this way. And every vector lattice is a distributive lattice with join and this meet. And the subset of vector lattice consisting of positive element is called a positive cone. And positive cone is directed preorder set with upper bound function join. And the linear functional is positive if fx is positive for all x in positive cone, in the positive cone.
Sorry, just to let you know, we have 5 minutes left. Okay?
Pardon?
We have 5 minutes left.
I cannot.
We have 5 minutes left. 4 by now.
That doesn't count, that's not fair.
I'll send him a message.
There are 5 minutes left.
Okay. And if we define R to be a linear Riemann integral, then it is a positive linear functional. And also we can define positive part, negative part, and absolute value in vector lattice. And the vector lattice is Archimedean. If x has x is less than 2 to the minus n y for some y, then y is negative. Okay. Then we can show that Archimedean vector lattice satisfy these two conditions. The lemma 22 hold classically for every vector lattice, but we need Archimedean property to prove them constructively. And the vector lattice is a topological vector. Okay. Something?
It's like Japanese AI.
Please continue.
Okay. The first condition is topological vector space with the uniform structure, and join is uniformly continuous. And third condition say that the positive cone is normal, which is in usual definition of vector lattice, classical topological vector lattice. And every topological vector lattice is Archimedean, and its completion is also topological vector lattice. And finally, we are going to go into integration theory. Abstract integration space is a vector lattice with a positive linear functional. Okay, that is a uniformly continuous function on the unit interval, and Riemann integral is abstract integration space. So in the following, we fix an abstract integration space. And first we define equal sub L, which is an equivalence relation on X in this way.
Sorry, can we get to the end here because we have the break? We have our coffee break here. So we're gonna need to finish.
Okay.
We're a little bit over time here, so maybe
Okay. And we can define a uniform structure in this way. And then L is a topological lattice, and we write L for the completion of that topological vector space and call an element of L an integration space, integrable function. And we can define integral as usual. And also, we can define another equivalence relation equal M, and also uniform structure, which is which consists of positive cone, product of positive cone and the natural number, and rho M and forcing relation are defined in this way. Then M is a topological lattice, and we write M for completion of that topological vector space, and call element of M a measurable function. And function, identity function is a uniformly continuous setoid injection of L into M. So we can, there is the uniformly continuous embedding from L into M.
I'm so sorry, do you have a final theorem that you can state, and then we're gonna need to go?
Okay, and then we can define some locally continuous mapping, mu, in this way. And then we can show the following, and for example, theorem 38, for a measurable function bounded by integrable function is integrable. And we can define convergence in norm and convergence in measure in this way, and then we can show that Lebesgue monotone convergence theorem. Okay, and also we can show Pato's lemma and dominated convergence lemma. And this is acknowledgement. Thank you very much.